catalyst. So, natural esters. The ester functional group is widely used in nature. Fats and also, by the way, I will be going through what I meant here and what I meant here and what I'll be meaning here. I'm just kind of reading it out so you can kind of get an idea of it, because maybe you read that out enough and you thought I have no idea what he's talking about. I'll go through an example to show you what I mean. I'll go through each section, but I wanted people to actually know what I was kind of going through here. Yeah, so the esters functional group is widely used in nature. Fats and oils. Vegetable oils and animal fats are esters of propane 1,2,3 triol, but in simpler terms, biologists will just call this glycerol. So all glycerol is propane 1,2,3 triol. At room temperature, vegetable fats are liquid, which are oils, but animal fats are usually solid. So an example of, actually no, let me just explain what that means here, right? So vegetables are liquid, but animal fats are usually solid, and that's because vegetable oils are usually unsaturated and have weaker van der Waals intermolecular forces. So because they're unsaturated, they have at least one carbon-carbon double, sorry, one double carbon-carbon covalent bond, and because of that, I think I mentioned this I should have mentioned this before, but when you have esters, when you have any groups, right, and you have a carbon-carbon double bond, that it kind of kinks the structure. The double bond kind of kinks the structure, whereas when it's a normal carbon-carbon single bond, right, it doesn't have that. It's always planar. But this carbon-carbon double bond kinks the structure, and it doesn't make it planar anymore, and it means it's harder for other of those, in this case esters, to stack up on one another easily. So you're forming less and weaker van der Waals intermolecular forces, and therefore there's less van der Waals intermolecular forces. The state of matter would be liquid. Whereas with animal fats, right? It's saturated. So there's carbon-carbon single bonds. The structure is being kinked. Therefore, it's more planar, and it's easier for these esters to more easily stack upon one another and form more of those van der Waals intermolecular forces, and the more stronger van der Waals intermolecular forces, and therefore it's more rigid, and the state of matter will be solid. For example, if you've seen a vegetable like sunflower oil, if you go to your mom's kitchen, see your mom's kitchen, that's quite stereotypical, isn't it? If you go to your kitchen, I shouldn't have said that really. I get roasted by this point now. If you go to your kitchen, right, you'll find sunflower oil, and that's or any vegetable oil, olive oil, sunflower oil, whatever oil you have, right, it's usually liquid form. It's liquid form. Whereas animal fats, like you can get if you get butter, right? Butter is an example of animal fat. Usually they take it from cows. They extract the fat from cows, but as that is animal fat in itself. That's obviously butter is solid at room temperature. Obviously put it in your fridge, but generally at room temperature, if you take butter out, it's solid, and that's because of what we just talked about here. Alright, and then the last thing here is soap. So soaps, you can hydrolyze natural esters to give soaps and glycerol. Glycerol is the most common name for propane 1,2,3 triol, and soaps are just salts of long-chain carboxylic acids. So here is glycerol, or propane 1,2,3 triol, and this is the displayed formula. So here I'm going to go through this part here about natural esters and actually forming the esters, right? So esterification, as I said, well, this is part when I say it's not a mechanism. You just need to know how it happens. And really, I'll give an example. Here's the glycerol, and here's a fatty acid. Right, fatty acids, obviously, there's just so many, because fatty acids are just carboxylic acids, right? And it's endless possibilities, because I just have the R group can be anything, right? But all you need to, this isn't really relevant. The only thing that's actually relevant when you're doing this esterification reaction is just this part here. Oh, actually, I want to use a highlighter. This and this. These hydroxyl groups are the things that actually matter in your during this reaction, right? And so all you need to actually do here. So I've got a little arrow. If I was to add these two esters together, so you add these, the alcohol and the carboxylic acid together, you would form this, right? So this backbone here would just stay the same. That's how you can just easily do this. But now I have broken, let's say I would have removed, I don't know which one it is, but either way, you don't have to really know which one it is. All you need to know is that a hydroxyl gets removed. You're getting at least, let's just say the hydroxyl from the alcohol is being released, right? It might not be correct, but you need to understand that a hydroxyl is lost and hydrogen, this is a condensation reaction. You're losing water, and then you're only forming this, you only have this oxygen here, and I'll have the other bond from the carbon, that's 2 bonds, and then you have your COOR, I guess, group, or your ester bond, right? So this here, we've lost that and that, so now we just have this. I'll keep it in green actually to show you where it is, and then that just stays the same. But this here, these parts here, so this part here, so this stays the same. The part that's not in red, it stays the same, right? So I can just pretty much just go ahead and just do the same here, and it's literally the same as you go down it. So it's very easy to do. Obviously the R groups can would vary. The R groups vary upon what compounds you have, but just knowing the overall trend here is just, it's just that. That's the only thing that really matters. Everything else will just stay the same. R1 and R2, right? So here's an example. I want you to try and do this. Reaction here. Given that I've just told you it, try and do this this esterification here. Pause the video now and try it. All right. I assume now that you've tried and you tried to do it. So yeah, unpause the video. I assume you've unpaused the video now and tried to do it. So this is what you would get. I forgot to mention, actually, that's my bad, actually. I forgot to mention, because you've taken out a hydroxyl group and a hydrogen here, my bad, you don't want to make this mistake, right? You're going to form 3H, you're going to form OH plus H, OH minus, I guess, and plus a H plus forms water, right? So, and you're doing it 3 times in this case, because it's propane 1, 2, 3 triol. You're going to form 3H2O. And that's quite important. That is literally a mark in the exam, because everyone forgets to write the 3H2O part. So remember to put this 3H2O part here, because you do form water from this reaction, 3 moles of water. Anyway, so if you've done that last one, you should have got this. As I said before, you can get a really long carboxylic acid, but this part here, this is not relevant. Remember I said before, it's just the hydroxyl groups. All right, so now I'm going to go into this next part here, which is about soaps. I didn't really do it in order, but, you know, doesn't matter. You guys already know I use this from Seneca anyway. So saponification, right? So, you know, so what is saponification? It is what you literally hear. This is how you form soaps. This is literally how you form soaps, in industry at least. Obviously, I have this probably a better way from before, but, yeah, at least in industry, you need to understand this, right? It's a hydrolysis. You're breaking down this compound using water, right? Or the hydrolysis doesn't necessarily have to be with water, but you can use at least you'd use at least this base here for this hydrolysis reaction. You not necessarily always have to be water. I know in biology you're generally taught that water is used for the hydrolysis reaction. In chemistry, whereas it's not actually the case, where you'd actually could have bases and acids are much better at hydrolysis, right? So in this case here, we have sodium hydroxides. This is the base that we're going to be using, and what it does is that we're breaking this bond here, right? We're breaking this, and then once we've broken this, I put this in color with color for a reason, right? To show you which part of the base is being used here and where it's going to go. So in this case here, I'm going to show you it's going to. I should probably use white. So this doesn't change. This never changes, right? oxygen, oxygen, oxygen. But we have now, we're splitting this back into an alcohol and into an carboxylic acid, right? So this is the hydrogen from the sodium hydroxide would go to the or forming this would be forming the alcohol here. We're forming the alcohol here, so we go to this kind of group here, which is kind of what I don't call this propanoate. Propanol. I guess it's an ion of sorts. It's an O minus really. I should really it'll be more like this, right? And it would attract this H plus. Yeah, and then that's how it would. You don't have to know about the mechanism all of that. You just need to. I'm just trying to explain to you why it's happening, but really all you need to know is that this is where it's going, right? We now have our glycerol, and now as for the carboxylic acid that we're forming. Now, it's not exactly a carboxylic acid that we're forming. It's more of a carboxylate ion, really, that we're forming here. And I'll show you why it's a carboxylic acid, a carboxylate ion. If I just get this here. So, I'm going to go just form this here. So, this part is the part we all know. We all accept that this part doesn't change, right? This part here doesn't change. And this part here doesn't change here, so. But, so now we've got this part here, right? So this would be so minus. The reason that I write it like this is because this would very quickly dissociate in solution. This is sodium hydroxide is a very strong base, so it strongly dissociates. Or say, what did I say? Sodium hydroxide is a very strong base, and it would dissociate, yes. Hence why it'd be good for this case. But this is a salt. Sorry, my bad. This is a carboxylate. This is a carboxylate salt. Sorry, it's a carboxylate salt that you're forming here. I'm probably confusing some people right now. We have an ion. This is an ionic salt, right? An ionic with positive charged metal ion, and our our negatively charged oxygen gas here. This is an ion. This is an ionic salt, and we call this a carboxylate salt, right? And carboxylate, and we know one thing we know about salts. Salts in solution would dissociate, right? And that's why you generally write it like that. But I mean, obviously you can write it as NaO, but I'd write it as NaO, but just for the sake of it, like just showing you that this would dissociate in solution. This is both. Yeah, so this is an amphipathic compound that you have here because it's both hydrophilic and hydrophobic. So the hydrophobic part, right, in this carboxylic acid part here, so the long chain here, this hydrophobic part, that's the part that's going to adhere to your dirt. So this is the reason why this is so good as a salt. So this is why it's so good as a soap. Because it's so amphipathic, right? The hydrophobic part can adhere to the dirt on your skin, or anything that's on your skin, right? And any excess dust or dirt, whatever that's on your skin, and then also I guess sweat as well, right? And then the hydrophilic part would adhere to the water. So this part here, this part here would obviously dissociate in solution, right? The sodium part would probably dissociate in solution, but remember, water is polar, right? Water's polar, so it would the O minus would attract to the partially positive hydrogen atom on water, and that would adhere to the water. So as this part is pulling onto some piece of dirt or whatever that's on your skin, it would get washed. It will get pulled, but it will get pulled by the water as it's going down the drain. So this part's getting attracted to the water. This part's is attached to the dirt, and then now as it's pulling away from your skin, as this molecule is pulling off your skin because of the water, and it will it will go down the drain with the water, and then this compound obviously as it is attracted to the dirt. So I kind of maybe muddled up the wording as I said here. So this will bind to any dirt on your skin, and then it will get washed away because this part here would be attracted to the water, and that will go down the drain as it's carrying dirt. And that's how you get clean. That's how soaps work. That's how they clean you, right? That is it. You can also you can add HCl. Yeah, so you can just add HCl. You can add HCl to this if you wanted to free your fatty acid as well. So you can add HCl to free your actual fatty acid if you wanted to. The last part here I wanted to talk about was biodiesel. So this is the part I here about the, go all the way up here. So biodiesel is made up of methyl esters of long-chain carboxylic acid. The long-chain carboxylic acids are reacted with methanol to make the esters. Biodiesel is made by reacting vegetable oils with methanol in the presence of a catalyst. Right, so we have our ester here, right? And we have our methanol, and we have our potassium hydroxide catalyst. That's what we would use. And it's the same principle as before. As I said before, you're just dissociating this compound down here from the H should go there. So that like in the saponification, this part stays the same. The only thing now that's different, it's the same kind of principle as before. The only thing that's different now is that you would be a methyl, it'd be a methyl ester, right? Methyl ester. So C, or I should probably use the coloring that I had before. So H3C O C. And then, yes, this is pretty much basic. I think everyone's this. Alright, so this video is pretty much done now. Hopefully you found this video helpful. I know I'm probably shite at explaining things, but as I said, I try.